Okay, everyone, I'm going to take up homework for the last 3 days. Okay, so we're looking at page 609 right now. That's where I'm starting. And I asked you to complete questions 3, 5, and 7. So it says, what is a carrying capacity? Why is it an important statistic when describing an environment? A carrying capacity is the maximum number of individuals an environment can hold, okay, without the environment getting destroyed and the animals dying or the plant dying. Why is that important in terms of describing an environment? Because after that, an organism reaches its carrying capacity, it can have really bad environmental consequences. Okay, so in other words, all the grass could be gone, a certain type of tree could be eliminated because the rabbits are biting all the bark, those type of things. And then the animals will starve if once their food source is gone. The human population is currently doubling every 40 years. Okay, based on what you have learned about population growth rates and carrying capacity, what questions should be asked of our society? This is usually one of the questions I pose at the very end of the unit when I'm teaching you. So this is really a thinking question, an application question. I might even put this on a test if you're writing a test. I just want to get your brains thinking, okay? This has slowed down, so good news on that. I don't think the doubling time is 40 years anymore, but it's just slightly less. And so what we have to ask ourselves, and this is the question I was posed, do humans have a carrying capacity? And you have an answer in your head right now, or maybe you don't. But I don't have an answer for that, okay? And I'm not sure that anybody does. So we don't know because of the things we can do in terms of technology, building skyscrapers. In other words, you don't have to have people taking up all the land. You can now build vertically instead of horizontally. What is our human carrying capacity? We really don't know if we have one, okay? There has to be some limit, but think about this. We've already have people in the world that are starving and living in horrendous conditions, okay, and losing children to illness and death and starvation, or obviously to death. So all of these things tell us that we might have reached our carrying capacity, and yet the human population is still growing. So this is why that's almost an impossible question to answer, but you would just apply what you've learned in the unit to answer that question. All right, and now with number 7, they give you a whole bunch of different n values. Okay, and they're telling us that we start out with a carrying capacity, or we have a carrying capacity of 1,500 shrews, and shrews are just a type of an animal. Okay, and their maximum growth rate is 1.0, so that's less than ours. And they take you through a whole bunch of n values and ask you, how is the population growth rate changing as a result of these n values? And so what I did was I solved some of these for you. Okay. And so what I want to show you here, and I only did 4 because you can get the point after doing 4. Here's our n. So if our population is sitting at the first part of the question, I called this A, okay, we have an n value of 100. So for those of you that are struggling in math a little bit, I'm just going to take you through this particular one a little bit more slowly. Here's our R max value, so we're going to have a 1.0, okay, and then we plug in 100. Your carrying capacity is 1,500, and then your n value again is 100. Okay, so in other words, our population is starting out at 100 shrews. The environment can hold 1,500 shrews, okay, and then we divide all of that by 1,500 once again. So when you're doing this math, this is how I do it. Okay, and I'm not meaning to insult you. Take this number, subtract that number, multiply it by 100, okay, divide it by 500, multiply it by 1. You don't have to do it in that exact order, but that's how I do it. I take 1,400, multiply it by 100, divide it all by 1,500, and then the 1 is going to be stable, so I don't even need the 1 in this case. But if this was anything other than 1, you'd need it. And so then your answer is going to be that you have a growth rate, a population change of 93 individuals. Okay, and then when you increase that n value, so now we're going to increase our n value to 275 individuals. Notice this number is changing. Okay, so this number is getting bigger. We have more individuals in the population as our n goes up. And I'm going to show you just 2 more things here. And it's going to seem very obvious to many of you. Okay, as our population is increasing, okay, our individuals are increasing. And so as you go through these numbers here on page 609, I did 100, 275, 450. Then I thought, okay, I'm going to show them 1,500 and not bore you with all these numbers. So if you understand these 3, you understand them all. And you have this picture of, you can take a picture obviously with this video or just pause it. when we get up to 1500, 1500 is our magic number. So I would say to you, what is that number? And you would say that's the carrying capacity. When the carrying capacity and N are the same, this is our N value, what would you think would happen to the population? And technically, theoretically, your population would not increase. You'd have 0 individuals added to the population. So if we were looking at our S-shaped curve, okay, there's our logistic growth curve. This is logistic growth. When we start with 100, and this is our carrying capacity, okay, is 1,500 individuals. When we were to start, and that would be on our y-axis, right? This is time, and that's number of individuals, and here's 1,500, okay? When we start with our n at about 100, okay, notice we're not adding very many individuals. We're adding maybe 93. And then when we look at 450, okay, that's 275. We'll say 275 is in that area, and then 450 is in this area. Now we're starting to see more growth. So the more individuals you have, the more growth you're going to have. And then when you looked at about 600, you would have been in this area of the logistic curve, and this is actually called the growth phase. Okay, again, in a better year, I would give you more detail. Okay, so over here, we're going to have the growth phase of that curve, and so you would have seen more individuals added, so your numbers would have been higher for 600, 825, etc. But when we get up to 1,500, which is our carrying capacity, now we're here, guys. Okay, this is where we are on the graph. And so when we get to our carrying capacity, you would expect that the individuals could not add, and the population could not add any more individuals to that population. Okay, but in realisticness and all reality, it does this kind of thing. And I looked for a graph that showed you that, comparing it to exponential, and I couldn't find one. So in reality, this is what's going to happen. It's going to waver up and down a little bit. Okay. All right, next set of questions, page 615. So on 615, I asked you to classify things as density dependent or density independent. Okay, don't worry about your classmates, you don't have them with you, but obviously you guys are in a group chat. A drought decreases the water level of a lake, thus decreasing its carrying capacity. Density dependent factors are things that are a result of the population size. Density independent are factors that have nothing to do with your population size. So this is going to be independent. Weather is density independent. Natural disasters are density independent. Mating is density dependent. Lynx prey on snowshoe hares. An increase in snowshoe hare population causes an increase in the lynx population. That is density dependent. Okay. A forest fire destroys a large amount, so we've got a natural disaster. That's going to be independent. Due to the introduction of a new species of fish, a lake becomes crowded. As soon as we see crowding, that's a density-dependent factor. The use of pesticide thins the shells of peregrine, falcon eggs and dramatically reduces their population size. That is going to be density independent. Okay, so they're showing you that pesticide is another thing that's independent. Increased water temperature causes many aquatic organisms to die. Okay, even though you might think it's competition for oxygen, and you could argue that, and you would have a really good point there, I'm going to say because oxygen is less soluble in warmer temperatures, that this is going to be density independent. So it's not a matter of the fact that you're all competing for the same oxygen, although that is completely true. I'm going to go with the other side of the coin and say that as you increase your water temperature, you decrease oxygen solubility. Okay, but honestly, if you want to argue that one, you could obviously win that. Okay, and argue that with me. So that was on that page. And then finally, as we finish up this unit, okay, we get to question number 2 on page 628. This is where I asked you to identify these organisms and their interactions, right? Okay, so here we're going to have a win-win, just super quickly. Different types of symbiosis. Symbiosis means living together. Mutualism is a win-win. So if I was teaching you this, I would say that's a positive interaction. Okay, so positive, it's a win-win. Commensalism is a positive, neutral interaction. Okay, so we've got the cattle egrets feeding on insects that would be normally bothering these guys. If the insects aren't bothering the elephants, then it's a neutral interaction for the elephant. The elephant doesn't care, but it's stirring up the grass, and these guys are feeding off of that. So you would see this in a nature channel. These birds hovering around these guys, because when the elephant walks, the insects jump and they get fed. So the birds, the egrets, are getting a positive interaction. They are getting nothing from it and not losing anything from it. And parasitism or predation, either or, is a positive, negative. So it's a win-lose situation. Okay? The parasite or the prey, the predator wins, the prey or the host loses. Okay? So looking at this, clownfish and sea anemones, win-win. Okay, they're both winning. Schistosomes and humans lose because this is our parasite. Blue whales and krill lose. The krill are the prey. Two trees living close together. I thought that would be a lose-lose situation because of competition. Okay, or it could be a win-lose because we don't really have something preying on another one. You could also argue win-lose because one's going to win over the other one. One's going to defeat the other one and win for the sun. All right? Okay, that is it.